Okay. Hello, everyone. My apologies for asking for your time available for a TA review session, but I still have to record because I just checked about my schedule. I will be very busy during this the rest of the semester, so I think I may not have time to have a physical lecture because yes, that's all. So, in the rest of the semester, I think every time I think there's a need to do some review, then I will record and video. Okay, so let's talk about chemical energy. So, in this video, I will talk some easy concept and one problem. And I think the other TA told me that um, last time when you guys had the quiz by Professor Yu, there are many of you have trouble to figure out what sign, which is positive or negative, should the energy, which especially work, should be. So in this video, I will explain about this part in my own way, and I hope I can help you more. Okay? Okay. So first of all, the universe is divided into system and surrounding. So the system is it's kind of easy. So when we talk about one gas or a reaction, that is the system. So let's take a look at this exercise. Hydrogen gas and oxygen gas react violently to form water, and this is we so-called the system. Okay, the surrounding is other than the system, which is when you look around the reaction, all around the reaction is the surrounding. Okay, so exothermic reaction. This is take a look at this definition over here. The scientific definition is that the system give energy to the surrounding. So in this part of the exercise, let's take a look again. Hydrogen gas and oxygen gas react violently to form water. So this is kind of easy to imagine that when the hydrogen and oxygen react with each other, it will have a lot of heat uh, released from the reaction. So we know that the system is hydrogen reacted with oxygen and form water. Then it will come out a lot of heat. Okay, an endothermic reaction is that the system gain energy from the surrounding. So, endothermic reaction, if we talk about heat, then we can simply talk about that we add some heat into the system from the surrounding. So, okay, when we are heating a cup of water, so for the water, if the water is the system, then we uh, the heating process is an endothermic reaction. Okay, so okay, next. Okay, let's talk about the internal energy. The internal energy is defined that we divide it into two parts. One is heat and one is work energy. Okay, so this is a little bit like when you're it's a little bit like the physics part. It's just like when you put a ball over here, and it came from a height h into the ground. And if the system is like this, then we can say that the energy is divided into two parts, like potential and kinetics. Okay, and the kinetics energy will be the kinetics energy will shown as speed, velocity, etc. And potential energy is shown in the height. Okay, but here is chemistry. We divided two energy. Is one is heat and one is work. Okay, so when you're like in high school, I think you will imagine that the Q is related to temperature. But yes, actually it is. But in this chapter, which is where we talk about internal energy and enthalpy, uh, we should focus on we should focus the temperature change more relatedly to internal energy and enthalpy. So I will stop over here for a minute. That when you talk about when we have a clue that is the change of temperature, the first thing you should think about is enthalpy change or internal energy change, not Q change. When we are talking about reactions, but I will talk about it with the problem later. So let's focus on the important part, which is the Q, which is Q part. Okay, so let's talk about the definition from the textbook. Okay, so when you exert a pressure from the outside, and there is a there is a volume change. The textbook told you that when you exert P and there has a volume change, the work should add a negative sign in front of the calculation because the volume is increasing opposite to the pressure. Okay, when you're looking about this, I think you will have a lot of problem that you cannot understand what the hell is going on. So let's talk about this. I'll give you an imagination for this. Okay, so first, so you imagine this. There is an object over here, and um, you applied a force on the object. What it will happen? It will add velocity. So it will add kinetic energy. So when you push a ball, it will be more faster and it gain internal energy. And what is the direction? Hey, you see, while this is not moving and you give it a force, and the kinetic energy will add, the speed will add as the direction you apply the force. So we can see from this part, when you applied a force on an object, the energy should be positive when we take this direction as positive. Okay, so let's take a look at another scenario. Now, there is a ball uh, motioning on this direction with a speed of v. And now you give this ball a force. Okay, so this is very simple to imagine. When this ball is moving toward this direction, and you apply a force in the opposite direction, what will happen? The energy will go down. The speed, which is the velocity, will go down either. Okay, so uh, you're in this part of example, you can see that when the force is the force direction is same as motion, the energy will go up. And in the contrary, in the opposite side, when this force is the opposite as velocity or motion, the energy will go down. Okay, you might think about, hey, what is this related to the calculation of the work in the system, which is gas? You don't know, but let's talk about this now. Okay, so let's talk about the part of work over here. So now here is a system. You see, sorry, not a system. Here is the surrounding, and the surrounding exert a pressure onto the system and make the system volume be more smaller. Okay, so you can see over here, you exert a pressure and the volume becomes smaller. Do you think it is related into the example I just taught? Okay, so when you exert the pressure onto it, the volume becomes smaller. It's a little bit like the pressure is moving, as the same direction as the volume becomes smaller? Okay, again, you use a force to move the ball, and the ball is moving as the same direction as the force. So you move the pressure, and the volume is moving the same direction as the pressure from the surrounding. So we can see that the work should be positive. The work should be positive. Okay. So another thing. So when you exert a pressure outside, but instead of making the system being smaller, the volume being smaller, expand. So maybe, I don't know, maybe the system inside is having a expansion, but for this force from the surrounding, what happened? It is applying work in the opposite, on the opposite direction of the volume. Okay, so when the volume expands, this is more like a liability, which is not good for energy. So pressure P will do negative work on the system. So in this part, hey, W should be negative, which is smaller than 0. Okay, another scenario from the quiz that you have recently took from the class is that, okay, here is a P. The problem give you, here is internally a P, and while V1 is the volume, initial volume, turn to V2 when V2 is larger than V1. Okay, now here's the million-dollar question. What is the sign of W? Okay, notice that the sign of W should be taken of the system. So we're talking about the system's energy change in the form of work. So what is the W, the sign? Is it positive or is it negative? Okay, I will tell you the answer. It's negative. Why is it? Okay, let's take a look over here. When the internal pressure is P, you expand. What happened? The P is expanding as the same direction of the volume. So as the volume being bigger, the P is actually moving as the same direction. Can you imagine this? Okay, like this, this, P, 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 P. The P is making it bigger. So now the system did positive work on the surrounding. Okay? The system did positive work on the surrounding. So if you did some work to the surrounding, then you will lose some energy. So the work of the system should be negative, and the work of surrounding will be positive because you gain a lot of energy from the system. Okay, another scenario. I think due to this part, you should be familiar enough now. Now? Okay, there's a contraction of the volume. So now, you did work. Sorry. There's an internal pressure on the system, and now the system's volume becomes smaller. And what happened? Okay, now the system's pressure is opposite side as the volume contract. Yes, contract. So in this scenario, the system did negative work to the surrounding. So if you did negative work to the surrounding, that means that the surrounding give the system some energy. So the work of system should be positive. All right? Okay, I'll talk through here. Okay, after the explanation, I think the imagination from working, applying the force on the ball should be helpful for you. But if you do want to have a more easier way to memorize it, okay. Now we're talking about, okay, I will write like this: system of work and system of the work of surrounding. So okay, when a system, its volume has go down, which means that the surrounding has did a positive work on the system. So if V system go down, the work should be positive. Okay, notice that this is the energy gain as the form of work.那用中文讲一次的话，这个东西的意思是我以做工的形式获得到的能量。Okay? So when the volume of system expand, the work energy as the energy in the form of work should be negative because you work on the surrounding. You make the surroundings volume turn down. Okay, so in this is two opposite side. Okay, I think it should be a little bit boring for some of you if you are familiar with this, but the other TA said you have problems solving this kind of problem, solving this kind of question. So I do my best. Okay, so okay, when the surrounding of the volume of surrounding has come down, what does it mean? It means that the system expand. Okay, 那如果说就是这个 surrounding 它的这个它的体积减少了，那意思就是说它的那个就是说意思就是说那个 system 它的体积是变大的嘛，对不对？ Okay, so the system should be negative because the system volume has expanded. Okay, when surrounding volume go up, which means the system gain work from the surrounding. Okay, I think I'll explain to you about this by example problem again. So okay, conversion of the L times ATM and joules. Okay, you have to know about that pressure times volume will have the same unit as energy. And how to exchange it? Actually, this is very hard to calculate if you don't have a calculator, but the professor insists that you should not have used a calculator. So I feel sorry about this, okay? But I have nothing to do about this. Okay, another easy, I think this part is very easy too. Okay, so another part of the energy form is enthalpy, and it is a state function. What does state function mean? It means that we only talk about the initial state and the final state. 我们只在乎在第一步的时候跟在最后一步的时候。What is your state? Which means is what is your temperature, what is your pressure, and what is your volume in the initial state, and what is your temperature, what is your volume, and what is your pressure in the final state. And we only need these numbers, which is the initial number and the final number. Then we can calculate the whole the enthalpy change. So from the example problem from later on I will talk about, you will find out that internal energy and enthalpy over here will not be affected by how did you come from the initial to the final，就是这个 H in enthalpy 跟 E internal energy 不会因为你走的路不一样，那你的数值就会改变，你不会因为你走的路不一样，你数值就改变。So again, enthalpy and internal energy will not be affected by the pathway you selected. Okay. And Hus law stated that the forming enthalpy of the products minus the forming enthalpy of the reactant should be the delta enthalpy. Okay. Okay. But now I have to add one over here that in the state of an if in the, as the state function in one certain state, a state, the internal energy has a state 2, and a state's enthalpy should be a state internal energy at plus the state pressure and the state volume. Okay, over here. Okay. All right. Okay. Here's now is we talk about the heating ideal gas as the constant volume as under constant volume and constant pressure scenario. Okay. Sorry, I did not pronounce it very well. Okay. I have let's see how do we say about this? Oh, okay. I'm sorry. Okay. In this part, we talk about the heat capacity in different scenario. The two scenario is constant volume and constant pressure. Okay, and we will focus on two different scenario. One is monoatomic. A monoatomic is you only have one atom as the gas, which means like helium or argon, etc. And diatomic is in one gas molecule, you will have two atoms inside of this, like H2, nitrogen gas, oxygen gas. But still, we are talking about ideal gas. So actually, when we talk about that CV of monoatomic would be 3/2R, or NCP should be 5/2R, and this is still for ideal gas, because we did not take into account about different type of gases complicate interactions. Again, while the heat capacity should be different between monoatomic and diatomic gas, but it is not correct that every diatomic gas or every monoatomic gas will have the same heat capacity. It is not correct. So we use computational stimulation about translational, vibrational, and rotational. So here is some computational assumption that helps us to find under ideal circumstance what is the heat capacity, but it is still very limited. You haven't concerned about a lot of scenario, like whether or not does the molecule like have hydrogen bond or something like that. So like H2O and S2O, these two type of gas should not have the same heat capacity. While even if we use translational, vibrational, rotational motions to calculate the CV of these two, if we assume these two gases are ideal, then the CV and CP of these two gases should be the same. But in real situation, it will not be the same, because why? Water gas should have hydrogen bond, 氢键, and S2O did not have any hydrogen bond inside of this. So the heat capacity of this should be more larger than this. Okay. Oh, sorry. Should be like this. H2S. I'm sorry. This has hydrogen bond, this doesn't have hydrogen bond, okay? Okay, let's talk about this. So under assumption that we use this motion to analyze that monoatomic gas should have the heat capacity under constant volume as 3/2R, and diatomic gas should have and diatomic gas I use different words, sorry. And diatomic gas or polyatomic gas because it have a lot of more complicated motions inside of the molecule. So the heat capacity under constant pressure and heat capacity under constant volume and constant pressure should not be the same as the monoatomic. So here's the part you have to memorize. For monoatomic gas, the CV should be 3/2R, and CP is 2/5R. And diatomic, CV should be larger than 3/2R, and CP should be CV plus R. Okay, about this, why CP and CV are always 1R behind? Why CV is always 1R behind CP? So let's take a look about this. Okay, we know that enthalpy is has a definition of the heat transfer under constant pressure, and we know that it is the same as like this, right? Okay, so now we know that internal energy can be the same as Q under constant volume. So let's calculate this. Now you have a constant volume is CV delta T. Okay, so now when you're going to calculate the enthalpy, you have to assume there is a constant pressure. So under constant pressure, the delta PV will be the same as delta nRT. So the moles should not be changing, but the T can be changing. So you can write like this. Okay, so now if we have assumption of 1 mole, then what will happen? It will be like CV times delta T plus R delta T, and it should be like this. And this will be end. So we know that under ideal gas condition, the CV and CP should not be the same if the gas are monoatomic and diatomic. Sorry, I'll speak this again. Monoatomic and diatomic has different CV and has different CV because the internal interactions are not the same. But no matter it's not monoatomic or diatomic, CV plus R will always become CP. Okay. Okay, I think I just covered this slide in the last page. Okay. Okay, for summary, the Q should be equal to moles times by heat capacity and times by the change of temperature. And whether or not the CP or CV depends on constant P or constant V. But I think this is a little bit sometimes you will confuse about this. So I think when it comes to temperature change, I think you should focus on enthalpy and internal energy first. Then, because when it comes to problems, it will only ask about Q. it will not give you the assumption. So I think you should calculate the E and H first, then you can calculate the Q by minusing. What do I mean? Because you know that this is N CV delta T, and you can calculate the W, and then you can use E minus W to find Q. Okay? Okay, let's take a look at the example problem. Okay, if you have a if you have problems due to this point, I think you should stop and think about it. And I think I encourage you to read the textbook more because this is kind of the way I understand this. So if you cannot, if you due to this point, if you cannot understand very well, I think you can email me. I'm Eric. You can email me. I will explain to you on my own. Okay. And the next time, if you do have any problems about this, and and you do and you do not know how to seek for help, you can tell me, and I can come to the class. After class, I can answer some of your problem. Okay. Let's talk about the problem. Okay. Consider two moles of diatomic ideal gas in initial pressure of 3 atm and an initial volume of 6 liters that undergo a change to 4 atm and 2L by two different pathways. Okay, so let's take a look at it over here. Pathway 1 is you come from 3 atm 6 liters to 4 atm 2 liters by this way. I will not read it. And the pathway 2 is the same. 3 atm 6 liters to 4 atm 2 liters. Okay, so this is a different pathway but the same ending. So let's take a look over the answer first. I calculate this. Okay, the answer of pathway 1, the enthalpy change is negative 35 and the internal energy change is negative 25. And for pathway 2, the change in internal energy is negative 25 and the enthalpy is negative 35. Okay, as you can see, the two pathway has different step because they process in different ways, but the final state and the initial state are the same. So for the two pathway, you should calculate at the end of your calculations, the internal energy should be the same and the enthalpy should be the same. But let's take a look over here. In pathway 1, the Q and W is like this, negative 37, 12, and pathway 2, negative 41 and 16 is clearly not the same, but the enthalpy and internal energy change is the same. So I think that let's take more closely look on the problem. Okay, so what I have covered is that if the pathway is different, then Q and W should be different. But if the final state and initial state are the same, no matter what pathway, the internal energy and enthalpy should be the same. Okay, so now diatomic ideal gas, which means like H2, N2, or O2. Of course, in real condition, these three gas should not have these gases should not have the same CV and should not have the same CP, but we have talked about this. This is ideal gas. So let's talk about this problem now. Okay, now pathway 1, notice this is diatomic, so CV should be 2 over 5R and CP should be 2 over 7R, 7 over 2 and 7 and 5 over 2. 5 over 2, 7 over 2. Okay, for diatomic ideal gas, this is the CV and this is the CP. But if the ideal gas is more like maybe ideal H2O or ideal N2O, the CV should be more complicated. Okay, so the first is okay. You start from 3 atm, and your volume has contract. Your volume being smaller, 就是你的体积缩减。So okay, the scenario is like this. Okay, so now what happened is that um, the P is moving. The P inside of this system is moving the opposite direction. Is moving through the opposite direction of the surrounding is compressing the system. Okay, again, your direction is over here, but the movement direction isn't the same. Okay, so that you are doing the system is doing negative on surrounding, which means surrounding doing positive on the system. So in this case, the W should be positive because the volume, again, the volume has become smaller. Okay, think about this again. Who has a smaller volume change? Whose volume becomes smaller? That guy will gain working energy. And who volumes got bigger? That guy will have negative working energy. So the surrounding has a bigger volume. The volume has expanded in the surrounding outside, not this. So the work of the surrounding should be smaller than 0. Okay, now I'll move on. Oh shoot. Okay, now over here, you have a volume change, so you can calculate the W. And because you have a volume change and you know about that PV will equals to nRT as you at two side delta, then you can find the delta T over here. And if you find delta T, you can calculate the internal energy and you can calculate the enthalpy. And after you find out the internal energy change, then because you have calculated the work, then you can easily find out what is the Q change. Okay, now, first, we know that W should be positive. So uh, here's a way for you to calculate. You can first, because you already know that W should be positive, so you can just do like this. Okay, 3 and 6 to minus 2, and this is 12. Oh, yeah, I think the answer is 12. But we have to use W is equal to negative P delta V. So in a real way that we write this down, we should negative 3 times the volume change is 2 minus 6 because you come from 6 to 2. So this is easy to watch. Negative 3 times 2 minus 6, and it will equals to 2 ATM dot L. Okay, now it's over. All right. Oh, and another thing is you should not change the unit into joules so quickly because it's very hard to calculate. And this problem did not tell you that you need to use the unit as joules, so I think it is okay for practicing. But when it comes to midterm exam, I think you should ask the professor that when we are doing the calculation, should we write down the unit as joules or we can use ATML? But for me, I think when you use the correct unit, I think it's okay. Okay. So now we have to calculate the temperature change. So now a little bit heads up because you know that we know CV and CP have have a term of R, and we know that in the ideal gas equation, there is an R over here, and the R should be 0.08 Q atm.L and mole K. This is the unit, and no matter what unit like this, it is very ugly. And when you're doing calculation, is like a nightmare. So when you're doing the calculation over here, keep the R over here. You do not want to calculate it so quickly. So PV PV equals to nRT is like this. Uh, when it comes to delta, you should use the final state to minus the initial state. So 3.3 3 times multiplied by 2 minus 3 multiplied by 6 over here should equal to what? 2 moles, okay? 2 times R times delta T. All right, over here. So it can be easily to calculate that the temperature should decrease, so for diatomic molecules, we know that CV and CP are 5 over 2 R and 7 over 2 R. So it can be easily to calculate that, okay, E should equals to negative 30 and H should be equals to negative 42. Okay, and the last part is the Q. We haven't talked about this yet. Okay, Q plus W should equal to internal energy change. So Q plus 12 over here, we just calculated it, should be negative 30. So Q should be negative 42. Notice that because this pathway, the step one is what? Constant pressure. So Q equals to QP and equals to enthalpy change. Okay, in step two, the volume does not change in the first step. Pathway one, step two, sorry. The volume does not change over here. So we know from the definition that work is equal to negative P dot times by the volume change. So if you do not have a volume change, we can take a look at the PV diagram over here. From C to B, from C to B, the value of work should be as the same of the area under the PV diagram. But from C to B, there is no area made in the path in the step two. So if you do not have any volume change, then it's a little bit like there's a ball over here and you give it power, but you give it a force, but it's not moving. So you're actually not giving it any energy. Okay, so if the volume does not change, that you will not get any form. You will not get any energy in the form of work to get energy. Okay. So if the volume does not change, there will be no W. But the volume the pressure has changed. So there should be a delta PV should be delta nRT. This part has changed, and this part has changed, so this part should be changed as well. And since that the moles and the constant will not change, so we have to change in temperature. Sorry. Okay, so in this part, final minus initial, so 4 multiplied by 2 minus 3 multiplied by 2 over here should equal to 2 multiply R multiply delta T. And after our calculation over here, we can calculate that T will equal to 1 over R. So after the calculations over right here, you can see that E should and internal energy and enthalpy should be equal to this calculation. N CV delta T, N CV delta T. Okay, so and by the W is 0, then you can find out that the Q should equals to internal energy, which is 5. Okay, now after you calculate step 2 and step 1, all you have to do is add it together. So in this part, step 2, the internal energy change is 5. So in step 1, the internal energy change is negative 30. So when you add it together, it should be negative 25. And enthalpy change in step 2 is 7, and in step 1 is negative 42. So when you add it together, it should be negative 35. Okay, and other part of this, I think you can be easily calculated by yourself. Okay, so because the pathway 2 is the same meaning as pathway 1, so I will leave it to you. And there are some example I put inside of here. And the Hess law part, because Hess law is actually easy, but a little bit important. So I will leave it in this PPT as well. Okay, so if you have any problems, you can contact me. But in the pathway 2, I will not explain so much now because it is basically the same as pathway 1. Okay, I hope this video will help you to find help you in understanding how to calculate the energy. So basically, when the system has expanded in the energy, the W again, the meaning of W is the heat, is the energy that gain in the form of work. 那个 W 的意思就是说，我以做工的形式获得的能量。So when the volume expand, the work energy of the system should be declined. And in the opposite side, you should think it by yourself. Okay, so this video will be over not by now. So if you don't have any problem, just email me again. Okay, thank you.